Hello everyone, I'm Ruihong from the University of Queensland. Today I'm going to share with you our work at ICDM 2022, Beyond Double Ascent via Recurrent Neural Tangent Kernel in Sequential Recommendation. This work is done with our colleagues at the University of Queensland. They are Helen Huang and Hongzhi. So today we're going to talk about one thing, it's called infinity. So many people sometimes will say that, okay, for a data mining model, when it becomes bigger, the performance will generally be better. So, but there are generally even more people who say that, okay, there will be overfitting. For example, in this figure, the horizontal axis here means that the model complexity. The vertical axis here means the loss. For example, the gray lines here is the training loss, and the red lines here is the cross-validation loss. So for example, we can see that when the model complexity is becoming larger and larger, the training loss will decrease, but the cross-validation loss will firstly decrease, then it will increase. So people will say that, okay, there will be overfitting here. So in our sequential recommendation problem, we do an experiment to further increase the model size to make the model complexity even larger. So here is our experiment result. They are visualized in these four figures. They mean four different data sets. So for the color bar here means the training epoch. So here we train every model in 20 epochs. So for the horizontal axis, it means the data complexity. So for example, 10 or 100 or 1000, they mean the hidden size of our neural network. And then for the vertical axis here, it means the model performance, and it's the MRR. So we can see that when the line goes higher, the performance means better. So one straight line in the vertical axis here means one experiment in one specific width of the model. So for example, we can see that when the width of the model is 10, the training is from light yellow to deep purple, and then the performance is corresponding to from about 0 to 0.02. So we can see that here is a trend. So the performance is, the trend is like this. It will firstly increase when we increase the model size, but it will decrease at some time. For example, decrease from here. It will begin to decrease from here, and also from here, and from here. The model performance will begin to decrease. But when we even increase the model size more, for example, to 1000 or even more, we can see that the model performance will gradually become even higher. So the performance, we can see that they are increase first, and then decrease, and then increase again. And we can even see that for this green dashed line, it means the when we apply early stopping for their best performance, or even we can just see the deep purple line here, which corresponds to the end of the training after 20 epochs. So we can see that they all give us this trend. It will firstly increase, then decrease, then increase again. So for example, for this green dash line, for this green dash line, or even for this deep purple line. So we call this phenomenon a double ascent. So it will ascend first, and then descend and ascend again. So can we make use of this phenomenon, or can we benefit from it? So it's kind of impossible physically, because we can just increase the model size to infinity. We have no such kind of hardware to put such an infinite model to this hardware to do computation. For example, no GPU, no CPU, or no TPU. So it's impossible to do it physically. But can we do that? If we really want to do that, do we have a method to do that? In this paper, our answer is yes, we can try to do that. So in neural network, there is one thing called neural tangent kernel. So what is a neural tangent kernel? So imagine the situation when we have an infinite width neural network. So for example, the width of the neural network is infinite. So if it's infinite width, and then it's physically impossible. Of course, we don't have such kind of hardware to host such a huge neural network. But in calculation, in mathematics, it has some good properties, good statistic properties. So what's the properties here? So when the weights of this infinite width neural network is initialized in Gaussian distribution with some very mild precondition for this neural network, the outputs of this network under initialization can be statistically predicted. So this is a very good property, which means that we can kind of predict what this neural network will do, although it's within the initialization. So this prediction is based on one thing called neural network as Gaussian process and then GP kernel. So so it means that the neural network under initialization is corresponding to an NNGP kernel. So what if we kind of train this neural network? This neural network can also be calculated of how it will perform, how it will behave after this training. So this training is not, as we know, as the SGD stochastic gradient descent. It's trained in mathematically based on a continuous time gradient descent. So under this situation, the infinite width neural network, the performance of it after training can also be predicted. So how is it predicted? So people do a derivation of this infinite width neural network. So they know that the training of such kind of infinite width neural network is equivalent to a kernel regression. And this kernel is called a neurotangent kernel. So they can be theoretically derived for many different types of neural networks. So MLP, CNN, or even RNN here. So RNN is important in our sequential recommendation because it's a sequence encoder. So in this work, we will look into the recurrent structure, of course, because we have sequence in sequential recommendation. So we firstly choose the recurrent neural network to as our initial try. So for RNN, firstly, we need to derive the general situation for recurrent neural network. They are corresponding tangent kernel called recurrent neural tangent kernel, short for RNTK here. And then, but it has some problem that cannot be directly used in sequential recommendation. So what is the problem here? So the first thing is that for general recurrent neural network, they will not care about the shared input-output embedding layer in our general usage of recurrent structures in sequential recommendation. So the first thing is that we do some extension of the RNTK. So the first thing is to calculate the RNTK within the shared input-output embedding layer. And the second thing is to we do calculate the RNTK under the zero padding situation, which will accelerate the calculation by a very large margin. And also in the final step, after we have the kernel to calculate the similarity between different sequences, we will use a simple KNN for prediction. That's the basic whole idea for how to use a recurrent neural tangent kernel in sequential recommendation. So here's a figure to compare the traditional finite model with our proposed, we call it an over-reg model, which use RNTK here. So for the left part here, we can see that for the finite model, traditional finite model, they will encode a sequence of user behavior, and then the output will be a match or a representation that can match the sequence with all the items inside the item set. So in our method here, we actually use the RNTK to compare different sequences. And then when we have a kernel calculates the similarity between these different sequences, we simply use a KNN, which based on this distance measure, a similarity measure to do the prediction here. So we can see that there's the difference between the overall structure, overall pipeline between traditional models and our model. So they will calculate a representation and then do the dot product matching between representation and items. While in our work, we just do similarity calculation between different sequences, and then we use this similarity to do KNN. So in our experiments, we evaluates the performance on 4 datasets, 3 from Amazon, 1 from Movie Lens, and then we use mean reciprocal rank and also the normalized discounted cumulative gain to evaluate the performance of different models. And the model, the performance is the higher the better. And then the baseline here we choose firstly is the non-learning methods. Most of them are based on KNN method. So firstly is item KNN, which just care about the item itself. They don't actually take the sequential information into consideration. And these SKNN and STAN are two recent methods that they use the sequential information for KNN method, but they are just calculating the item frequency. And then we also take the shadow method, which BPR, matrix factorization, and we also use some very classic and typical advanced deep learning methods, for example, GRU for reg and SAS reg using self-attention, and BERT for reg using BERT model to train the sequential recommendation. And then we firstly see the overall performance here. So we can simply see that overrec, that is our proposed model, is better than the methods using standard finite sequencing encoder. For example, we compared our overrec with this GRU for reg using GRU, and then SAS reg using self-attention, and BERT for reg using BERT. So we can see that the overrec method, using the RNTK, which is not a finite model. It is a kind of infinite model, and it has some higher performance than this traditional finite model. And then we also compared our overrec model with the other types of method that based on KNN, for example, this item KNN or SKNN or even STAN. So we can see that although we are using KNN methods in the last step to do the prediction, we can see that our method overrec, it actually has some better similarity calculation between different sequences, because we can have a higher performance compared with them. And then we also see that when we use NNGP as the similarity measurement, which is the recurrent neural network under initialization without chaining. It's still an infinite method, but it's just under initialization. We can see that our overrec is has some better performance than using NNGP, because RNTK is actually corresponding to the infinite neural network after training, but NNGP just it's just the infinite neural network under initialization. So we can see that performance is for overrec is actually higher than the NNGP here. And we also do a visualization of this double ascent. So firstly, we can see that on the left, we have 4 data sets here. So this one, and then this one, and then this one. We can see that from their first figure, it's the training loss. So we can see that for every model with different complexities, different model size. So the horizontal axis here means the model size. So for every model here, they are well trained. And for model with large model size, they even have a more well-trained situation. They have reached a lower training loss. And then for all of them, they have the same chance here. But we can see that after well-trained different size models, we can see that double ascent happens for all of these 4 data sets. And we can see that this purple dashed line is the performance of our overrec model. We can see that it can, for different data sets, it actually will even reach the infinite width situation, or even it will have some higher performance than the very large model. So we can see that the overrec can actually corresponds to this kind of neural network in very large model size situation. And then we also compare our model with different KNN methods. For example, here, the blue line here means our overrec model, and then the orange line here, the cross line here means the our infinite model with NNGP without chaining. And then the red line here means the STAN, just which uses item frequency with time effects to calculate the sequence similarity. And also the green line here just simply use the item frequency in between different sequences. So we can see that and then the horizontal axis here means different types of KNN methods. So for example, for weighted Y here, it's just simply use the last item as the prediction. And then for the equal item here means that they will simply they'll simply use the every item within the sequence to do prediction. And for the weighted item, they will further take the time situation into their prediction. And so we can see that weighted Y is a very direct, straight method that they just simply use the last item as the prediction. So it requires a more accurate similarity measurement. So in our method, we can see that using weighted Y, this using infinite neural network model can have a very high performance compared with other models. For all of these data set, we can see that blue and orange lines have higher performance. But with this equal item or with weighted item as the prediction, we can see that they are more suitable for not that accurate similarity measurements. If we are for example, for SKN, for STM, they are just using item frequency. So this kind of similarity measurement is not that accurate. So in that situation, they need to use some other types of KNN method. So we can see that in our method, the similarity measurement is accurate. We can just simply use the last item to do the prediction, and it can have a very good performance. So our conclusion is that we observe that there is a double ascent in sequential recommendation. And then we also say that, okay, when we use recurrent neural tangent kernel, we can benefit from this double ascent, and we can do a very high performance in sequential recommendation. So here's the reference, and thank you so much. Thank you for listening to our talk. Thank you.